Okay, friends, let's start lecture 17. Today we are going to do some elements of group theory. The reason is that the group we have seen so far to understand group of transformation group of symmetric transformation properties, symmetric transformations, which we have seen is essentially so far for electromagnetics theory. It's a very simple unitary group. Essentially, it's a unitary group of one dimension, which is essentially a local phase rotation of the phase locally. Locally here it means depending on the space-time point actually. Now, but if you want to understand other things like for example strong interactions and this group would not be sufficient. You need to understand much complicated groups, so which are not more than one dimension. So typically they are two dimensions for weak interactions or ultra weak interactions, or three dimensions for uh, strong interactions. So today we'll try to understand what these unitary groups are, what their structure is, and what does a representation mean. So these are the issues which we'll try to cover in the next two lectures. So to begin with, I think I revised earlier that what does a group mean? So group is just a set of elements group group G is just a set of elements. So it is just some elements, say A, okay, such that they satisfy the group axioms, okay, group axioms. So if it is if the group elements are discrete, the elements could be discrete, so in that case, say for example G would be something like 0, 1, and so for example, so n. So in this case the order of the group is something like, here in this case it will be order of the group is n plus 1 because order of the group is nothing but the number of elements in the group. So it's just the number of elements. In the case of continuous group, in this case the number of elements is infinite essentially. Is infinite. So this sets so the examples like for example, let's try to give an example of continuous groups. So if you have a group element like something like say example of a continuous group would be something like uh, e power I theta. So the same example where theta goes to say 0 less than or equal to theta less than or equal to 2 pi. So this is a group in which the theta is the element and the theta can go from 0 to 2 pi, This is an example of another group which is a continuous group. It's a continuous group. Now, so these elements I said satisfy a bunch of axioms, which I think we covered it several times, I think earlier also. The axioms are, I'll just cover it again. One is closure. You all know what it is. Associativity, inverse. Okay, maybe identity I should say first. And then inverse. So these are the axioms of the if all the group satisfies this axiom, all the elements in the group or the set satisfies this axiom. So this means that the set G has these elements satisfying all these axioms. So for example, closure means say A star AI star AJ, okay, also belongs to G for all AI AJ belong to G. Okay, so if you have this property satisfied like closure, okay, then associativity, which is again, as you know, I don't have AI star AJ star AK, AI star AJ star AK. If this is satisfied, and then there is also identity. So this means AI is this group element. This means that uh, mm, mm, okay, okay, I'll come to it in a second. Okay, I'll inverse AI star AI inverse is equal to AI inverse star AI is equal to E. Now this star which I used as the group multiplication law, the star is essentially, now this could be a group multiplication law. In general, what you can do, you can define a group with set of properties. Okay, you can say, okay, I have a group whose elements are essentially closure, associativity, identity, satisfy all these properties, and there is some group multiplication law which is given by this, which satisfies all these properties. But I don't say what these elements are. These are abstract elements. You can always have something called an abstract elements, abstract group. So you don't say what these elements are. Typical examples you can really show they exist in, say for example, in discrete groups. So in discrete groups, what happens is you can always write uh, abstract groups and define your group with that. And most of the time, the properties of this group depend upon the order of the on the order of the element of the group. Like for example, if you have only two elements in the group, so G is equal to A1, A2. Now, if you say that A1, A2, okay, are only it's a order 2 group, okay, A1, A2 form a group. So what it means? So now, first of all, you need to have A1 A1 star times A2 should belong to group, should also belong to G. Okay, then you should have A1 star A2 times A1 or any other element essentially, and A2 star A1 times any other element should also belong to the group, same group. And so then you also have identity and inverse. So all these properties have to be satisfied by this group for this discrete group. So in this case what happens, so what is given by the order, what are the options you have for the group? Say for example, if you just take them to be A and A square, okay, will this work? Okay, so such that A square is equal to E, say for example, or A its own inverse, say for example A times E is equal to A times A is equal to E, A square is equal to E. So you can think of what are the possible options you have, okay, what these elements would be. Essentially there are not many options. Okay, what is the group multiplication law, for example? So let's take an example. Okay, so now this is, so the abstract group, this is the abstract group, say for example. Now I want to look for what are called as representations of this group. Representations are nothing but vector spaces which satisfy the same group multiplication law. Now let's take, okay, so that means that you can have several groups which have the same properties as the group G. Say let's just take A is equal to 1, A2 is equal to minus 1. Okay, A1 times A2 will also belong to this. Okay, A1 times A2 also belongs to the A1. What is the inverse of 1? So the 1 square is equal to 1, minus 1 square is equal to, so 1. Okay, minus 1, so 1 into minus 1 is equal to minus 1. Okay, so everything, the simplest representation of this G is nothing but G is equal to plus 1 minus 1. This forms a group. This forms a group, but this is a representation. So this is a representation in a different vector space, in a different space essentially. So this group is a representation of this abstract group. This is the abstract group. So where we don't specify what these elements are. So I am not going saying what these elements are, what is meaning their numbers, objects, what this are. This could be anything actually. This could be flowers, this could be any objects you want essentially. But so we don't specify what these are. These are just some abstract objects. But the same thing you can, now you can have a representation. Okay, so these representations are, say, one example I gave you is essentially with G is equal to plus 1 minus 1, which has the same properties as the group we have seen earlier. So this is a G2 group. Let's say call it as Z2. Actually it's a Z2 group, also called cyclic group. As an you can also have a cyclic group actually in this case. There is one more representation of the same thing with finite number of elements. Okay, so the representations are most of, okay, so this is sort one dimensional representation. So these are sort of representations which are simple, which are essentially simple. Okay. Now, to be more accurate, let's me call if you have a group G with elements G, okay, which satisfy the group axioms, then D of G is a representation of the group. So it is also a set, okay, it's also a set of another set of objects, okay, it is another set of mathematical objects, typically most of the times matrices, numbers or something, such that D of G1 star G2 is equal to D of G1 star D of G2. So this G1 is a representation of the element G1 in the original abstract group G. G2 is the representation of the original abstract element in G2. So D of G2 or G1 star G2, which is also belongs to the original abstract group, also has a representation. So the representations follow the same group multiplication law as the original group elements. So the group multiplication law as the original defining what do you call the abstract group elements, whatever they follow, the representations of them also follow the same thing. Now we can write similarly we can write another representation of G, which is also the same thing as earlier. So which can be 1a, such that a square is equal to 1. This is essentially the same thing. Okay, it could be a could be anything such that a square is equal to 1. Okay. Now in this case we are calling it as a cyclic group. Okay, cyclic. These are all discrete groups actually. So initially I said there could be two branches of group. Okay, before finding it. So the representation, this is also another representation of the original abstract group. This is also some sort of an abstract group, which it comes out just from following the group axioms. In a more general case, okay, if you have a group, say group of elements, say G, Gi, okay, they could be discrete or continuous. The representation is a set of all matrices. It's a set of all matrices such that this bunch of all matrices, okay, this bunch of all matrices, so this would be some D of G1, D of G2, D of G3, D of G4, and so on. These are all matrices. So the representation of a general abstract group, it could be any group essentially, depending upon whether it is a unitary group, orthogonal group, there could be any. In addition to following this bunch of axioms, it could have other what do you call defining properties of this group. Say for example, okay, whether it is a unitary group, continuous group, discrete group, whatever essentially. Okay, in such a case, there could be something called exceptional groups and so on. So the representation is some sort of a mapping from this group elements to a group of matrices, to a group made up of matrices which satisfy not only the same group axioms and under the same multiplication law, but also satisfy the some sort of whether they are unitary or whether they are orthogonal, so on. So essentially all the rest of all the properties of the group elements. Okay, so all the properties of the group elements should be reflected in this representation. So there could be any kind of representations. So what people are interested in is something called the irreducible representations. That means these are representations which are defined by their dimension. So the same group, say for example, could be represented by one dimensional matrices, two dimensional matrices, three dimensional, n dimensional matrices, without spoiling any of the properties of the group elements, essentially of the, okay, of the group elements. Okay, so these representations can be any n dimensional, any dimensional. Okay, okay, in some, okay, so this leads to some confusion in in some cases which we will see. So which I'll try to solve. So d of g1, d of gn. Okay, now this the representations follows the group multiplication law plus most of the other properties of the group. If you want the defining properties of the group. Okay, and um, furthermore, the representations are classified in terms of the dimensions.